Okay. The fundamental theorem of calculus tells me that to solve a definite integral, I need to take an antiderivative. That means that antiderivatives are tightly connected with our process of integration. So why not use an equivalent notation? I'm going to define a new version of this symbol. This is a definite integral because it has a place where it starts and a place where it ends. This integral is going from A to B. But if I just say I want an antiderivative, then I need something that isn't bounded by specific locations. So I'm going to get rid of those two limits. If I write the same symbol, just without the A and the B, I'm going to call this an indefinite integral. And since our differential here, dx, means I'm working in the variable x, I'm actually going to call this the indefinite integral of little f of x with respect to x. I am thinking about what happens as I add up in the x direction. But we're going to use this symbol to mean the general antiderivative of little f. So the only thing that's missing here are the two numbers to plug into. And in a very real sense, that means that every definite integral that we do is first solved by finding that antiderivative by really doing an indefinite integral. And that's part of where our notation comes from. I can think of the integral from a to b of little f of x dx as telling me to do the indefinite integral and then plug in a and b and subtract. And that means that a lot of what I am really doing when I do integration, when I integrate at all, is I'm finding antiderivatives. So I'm going to say that the best thing we can do is take our derivative rules and rewrite them in this language. On page 410. I got a table. And this table really combines almost everything we've done as derivatives, just backwards. Best part, a good portion of this is on formula sheets. Sine, cosine, secant squared, cosecant squared, secant tangent, those six right there, they're on our formula sheet. So is this one, but it's written in its derivative form. If you pull out the formula sheet from the last exam, you'll see it written the derivative of a to the x is a to the x times ln of a. That's the chain rule in action. These two are also on the formula sheet because they are our inverse trig functions. And these two we didn't cover on purpose because hyperbolic functions are annoying and they're written in terms of E anyway. So I really only have to remember the E rule. So I'm never going to use hyperbolic functions in this course. So really the ones I have to remember are up here. But take a look at that first one. That first one says if you have a constant, you can pull it out front. That's our derivative rule. This one says if I'm adding, I can separate and do each piece separately. That's our derivative rule. This one says that when you integrate a number, the slope is 2, the function is 2x. The slope is 7, the function is 7x. Piece of cake. That's the power rule. And that's the exception to the power rule because it says right here, n can't be -1. If you have x to the -1, that's 1 over x. So that's every power of x. And that means that with this in my head, really only have to remember 2 rules. All the rest of them are effectively the same rules we've been doing. But that means I can ask questions like the following. If I see this, it doesn't look like I've asked a question. I've just written down an expression. But what this expression is asking me to do is to find the antiderivative of 10x to the fourth plus 2 secant squared x. Typically, the instruction that goes with this is integrate. So perform the integration, which is the act of finding that antiderivative. What do I get? Oh, I'm going to start with this part. What's something whose derivative is secant squared? You either need your formula sheet or to turn to page 410 in the textbook, which is where that table is. Now, this is me being pedantic. I've decided I'm going to separate all the bits. So since I'm subtracting in the middle of my function, I can turn that into 2 different integrals, subtracting the 2. I've got a 10 in the first one, I can pull it out front. I got a 2 in the second one, I can pull it out front. But now I ask the same question I just asked. What's something whose derivative is secant squared x? Bingo. What about x to the fourth? Exactly. But wait, there's more. What has to go on the end? C. Plus c. And now if you really want, you can simplify here. I get 2x to the fifth and 2 tangent of x plus c. By the way, when I took calculus, if I'd written that, my high school calculus teacher, Maria Soto, would lose me a point. Every time I forget to write the plus c where I needed it, I lost a point. I got a homework score that was negative. She was really I haven't forgotten a plus C since. Now, sometimes I'm going to have to do some work to get the derivative to a state I am looking for. So let's consider this problem. Tomorrow, I'll learn a different way to do this. But let me start with what I got here. I don't have any derivative formulas for division. Sorry, any anti-derivative formulas for division. I know how to do the quotient rule, but if I want to end up here, I mean, this is where I'm going to end up from the quotient rule, I figure out what quotient this is. That's going to suck. I don't want to do that. So let's do some rearranging. I'm going to take these trig functions and rewrite them in other trig functions. Because if that's sine squared, that's really sine times sine, so I'll split it into two separate signs. Of what possible benefit is this? I know that when I've got a cosine, its antiderivative is sine. And when I've got a sine, its antiderivative is minus cosine, because the extra minus sign that shows up. But I've got cosine over sine and 1 over sine. Wait a minute, what's 1 over sine? That's a different trig function, isn't it? What trig function is 1 over sine? I was going to say inverses are arc sine and arc cosine. I know it's sine to the minus 1, but that's not the same thing here. This is why I don't like that notation. I keep using arc. But 1 over sine is a different trig function out of the basic 6. It's cosecant. And cosine over sine, cotangent. So I can rewrite this minus cotangent times cosecant. And all of a sudden, bing, 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 bing. Minus cosecant cotangent's right here, isn't it? Which means I know the antiderivative of this, because that's on my formula sheet as a derivative. Oop, not dt. I did my antiderivative. The dt goes away. What do I put at the end there? Plus c. So it is incumbent upon me to, if I see something that I don't recognize, figure out how to make it something I do recognize. I don't like seeing quotients in my integrand. Because trying to figure out what quotient rule ends up here just makes my brain hurt. Quotient rule is one of the worst rules to try and work backwards because of how complicated it is. We'll find other ways to deal with it. Most of them involve rewriting quotients as products. So why don't we take that approach here? If I were to rewrite this quotient as a product, what could I do? Okay. But now, Jack, I think I want to steal your idea that you tried to do with the sign up there before. If I've got that y cubed on the bottom, how can I rewrite that? If I write it as y to the negative 3, then I can distribute. What happens when you multiply that through? What's the algebra? And that's something I can do. That's power rule. All I have to do is remember that when I'm multiplying through, I add powers. Presto. You could also not rewrite. You could say, I'm just going to go directly, since this is one thing on the bottom and two things on the top. I could write y over y cubed, and then 5y to the 7th over y cubed. And when I'm dividing, I subtract powers. That gives me y to the negative 2. That gives me 5y to the 4th. So this is another option that will get me to the same place. But now I have the power rule. So my integral is, I'm doing the integral. I don't need the integral symbol anymore. And there'll be a plus c at the end when I'm all done. What goes here? This part's easy. What's the antiderivative of 5y to the 4th? Say again? Y to the 5. Because it'll be 5 over 5, right? Y to the 5 over 5, but there's a 5 out front that cancels out. It's this part. Same routine, add 1 to the power. But that makes it y to the negative 1 on negative 1. Well, that's just a minus sign, right? The following step is not required. A negative power means it goes back on the bottom, right, Jack? And the minus sign that is currently down here can be put out in front or on top. That's perfect. Now, if I'm doing a definite integral, fundamental theorem of calculus says that if I want to do this problem, the first thing I need is the antiderivative. But I just did that. So I can literally take this expression that I've already computed and plug in the top and plug in the bottom and subtract.
I dropped the plus C.
Is that allowed? Why?
Because when you would do the difference between them, it would be 0.
I'd have a plus C and then I'd have minus and another C. So I add the C and I subtract the C, it cancels out every time. You can pick any value for C you want, it's always going to cancel. So you might as well just throw the damn thing away to begin with. Pick the value C is 0. And off we go. Now, if you don't believe me, we can actually put it back in and you'll see it subtracted from itself. But now I put in 2. Now I put in 1. And if there was a plus C here, there'd also be a plus C in here. So C minus C, they're going to cancel. Every time. So wait a minute. Negative 1/2 plus 2 to the 5th. 2, 4, 8, 16, 32. Minus negative 1 over 1, that's negative 1, plus 1 to the 5th. 1 times 1 times 1 times 1, that's 1. Wait a minute, negative 1 plus 1, that's 0. So I get 31.5. Questions? Now here is another case where I'm going to tell you that the instructions on the problem matter. Because often I will see this problem and it will say, give exact values. If I want exact values, that means I need to know the exact values from the trig function. And that means from my unit circle. So here's where my trig value is going to come back and bite me in the ass. I need my unit circle trig values here. Remember your hand trick? Does anybody know the hand trick? Oh, I get to teach you all the hand trick again. Put down your hand. You've got your pinky and your thumb. Well, that's 0 and 90 degrees. You've got 3 fingers in the middle. So that'll be 60 degrees, 45 degrees, and 30 degrees. But I'm evil. I like radians. In radians, that's 0 radians, pi over 6, pi over 4, pi over 3, and pi over 2. Which letter comes first? C for cosine, S for sine. C comes first, right? C. I'm going to count up from here. Which angle do you want the cosine of? Pick an angle. Which angle do you want the cosine of? 30 degrees. Bend in that finger. You got 3, you got 1. Cosine, sine. Square root of 3 over 2, 1/2. You want 60 degrees? 1/2 root 3 over 2. You want 45 degrees? Square root of 2 over 2, square root of 2 over 2. Take the square root of the number of fingers that are left. You want 0? Cosine is the square root of 4 over 2. Square root of 4 is 2. That cosine is 1. The sine, there are no fingers left. The sine is 0. Same thing works for 90 degrees. There you go. They're right here. As long as you have your hand with you, and none of you look like you could leave your hand at home at the moment, you're good to go. If you want to do cosine, you count this way. 0, 1, 2, 3, 4. Take the square root, divide by 2. You want to do sine, you count this way. 0, 1, 2, 3, 4. Take the square root, divide by 2. So, the reason I'm telling you that is so we can do this integral. Let's do this integral now. What is something whose derivative is secant tangent? Out comes my formula sheet again. Something whose derivative is secant tangent. The derivative of secant is secant tangent, so the antiderivative of secant tangent is secant. Oop, that's a 3 on the top, not a 2. Now, I don't know about you, but the trick I showed you just now only works with sine and cosine. So if I want secant values, I need to write it in terms of cosine or sine. What is secant as one of those functions? 1 on cosine, which means I need the cosine numbers, right? So this is going to be 1 on cosine theta, pi over 4, pi over 3, which is 1 over cosine pi over 3 minus 1 over cosine pi over 4. Cosine of pi over 3. Cosine is top to top. So cosine is 1/2. Cosine of pi over 4. Root 2 over 2. So flip this fraction out of the bottom and you get 2. Flip this fraction out of the bottom, you get 2 over root 2. Wait a minute. 2 divided by the square root of 2. What's 9 divided by the square root of 9? What is the square root of 9? So 9 divided by 3 is 3. What's 4 divided by the square root of 4? Because the square root of 4 is 2. 2 divided by the square root of 4, 2 divided by the square root of 2 is the square root of 2. Because there are 2 of them down up here. This top is the square root of 2 squared. One of them canceled out. So I get 2 minus the square root of 2. I don't care which version of this you stop at. But if I look in the back of the book, that's the answer in the back of the book. You'll notice what this is not. This is not 0.59. A decimal is not an exact value. If you see a problem like this and it says give an exact value, don't give me a decimal unless it's 1/2. Questions? The same thing would apply here. Boy, does that look crappy now. Cosine of x dx. E is one of those numbers that is going to give me crappy decimals all the time. So if I see this problem, it's almost always connected to give an exact answer. So that means if I see e to the something, I'm going to leave it as e to the something. Unless it's e to the 0. What's e to the 0? That's a nice easy number to deal with, 1. Otherwise, I'm just going to leave it as e to the whatever. So let's do this antiderivative. What is the antiderivative of e to the x? Wait a minute, what's the derivative of e to the x? Which means its antiderivative is the same thing. The 2 stays out front, I get e to the x. What is the antiderivative of cosine? Sine. The derivative of sine is cosine, so the antiderivative of cosine is sine. The 4 stays there. Now I just plug in the numbers. 2e to the 5th plus 4 sine of 5. That's disgusting. Minus 2e to the 0 plus, wait a minute, what's sine of 0? Scroll, 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 scroll. What's sine of 0? 0. So I get 2e to the 5th plus 4 sine of 5 minus 2. Now, if you want to give me an approximate value for this, you could plug this into your calculator and tell me this is roughly whatever it turns out to be, roughly 291. But if I want an exact answer, I want you to leave it like this. Questions? Most of the time, I think of an integral as a net change. Oops. So depending on the setting I am looking at, I can think of the way something in that situation changes. I have a volume function, V of t. The amount of water in a well. The derivative of V. What does this represent? What does the derivative mean here?
Change. Volume of time.
Change in volume with respect to time, which is the rate of water being taken out of this well or put into this well, right? If it rains, V prime should be positive. If it's dry and I water the lawn or take a shower, V prime should be negative, right? Okay. So let's think of the following. Let me actually be more specific. I'm going to go ahead and say over time in hours. I didn't say it up here. We're going to let T represent hours. And T equals 0 is midnight last night. So what does this represent? Don't give me a number. Can't give me a number because I don't have a formula for V or V prime or anything like that. But what does this represent as an idea?
The end and start of the day.
The what for the whole day?
The changing.
The total effective change in the water in the well, right? This adds up all the changes that happen throughout the day. We could say this is going to be V of 24 minus V of 0, which is the volume at the end of the day at midnight tonight compared to the volume at midnight last night. Did we use more water than we gained? Or did we gain more water than we used? Or did we break even somehow? The phrase I want to think of this is the net change in water level in the well over the period of 24 hours. But what I did is I added up little changes along the way. That's why I looked at V prime, because that's a rate of change. So if I add up all the little changes, I get the total change. This is the fundamental theorem of calculus part 1. When we thought of that area and we took its derivative, we got the little bit of change on the end of our picture. If I add up all the little changes, oh, that's why this is a prime in here. It's a rate of change. It doesn't have to be. I have a cylinder. And this cylinder has a gas source at one end. Imagine, if you will, a little piece of warm iodine at this end that is sublimating into gas. Over time, it will eventually fill the cylinder with gas. There'll be no solid. If you don't like the idea of this being iodine, think of it as if it was dry ice or something, right? Slowly you're making gas. But at this moment, while there's still a lump at one end, there's a density function. I'm going to mark this end of the rod as 0. And as I go to the left, that's bigger and bigger values of x. And I have a density function. Imagine taking a little slice 1 centimeter thick and saying there's this much volume of gas, grams per cubic centimeter, right? That's a density. But let's add them all up. What is the integral from 0 to, I don't know how far is, how big is this rod? Let's make it 2 meters. What is this going to represent? Think about my little slice. If I take a slice here, looks like there's very little gas in it. If I take a slice here, there's probably more gas in it. If I take a slice at this end, there's a lot in it, right? But if I add the slices up, I'm totaling the amount of the chemical, aren't I? That'll be in grams. Because each slice will be a certain number of cubic centimeters, right? Grams per cubic centimeter times cubic centimeters is grams. I add up all the weight. I can tell you how heavy this tube is. Imagine, if you will, that instead of being a hollow tube, it was a solid object. But it was made of a material that was denser at one end than it was at the other. I don't know, like a golf club with a shaft of varying flexibility, or a baseball bat with varying thickness. Well, I could think of the total weight as adding up all the weights of the little slices. Same idea. This idea, though, is referred to as linear density because your density only changes as you go down the line. A cost function, right? C of x. we gave a name to this function. What did we call it? C prime? A business specific name in terms of cost. I believe this is back in chapter 3, section 7-ish. Somewhere in that range. Examples of derivatives in business and social sciences. Flipping pages should be happening. Scrolling through the textbook should be happening. It is a rate, but that isn't what we called it in this case. There was a very specific name we gave business derivatives for cost, for revenue, and profit. But it is a rate. That's just not the word we used in this case. We called it marginal. Marginal cost, marginal revenue, marginal profit. And the reason I mention this is because in the real world, figuring out marginal cost is usually pretty easy. If you make sneakers, then you know the cost to make one more pair of sneakers. You know the labor cost, the material cost, the time crunch to do one more pair. Let's say you're making 50 pairs a day. You want to make 51 pairs. You can figure out how much more you need to spend to get people to do that one extra piece of work. That's actually really easy to calculate. But then something like this what does that represent at my shoe factory? What does it mean for my shoes? The what between 150 and 100? The total change in cost. Add up all the little individual costs, you get the total change, the net change in cost. To raise production from 100 to 150 units. So if I know, because I can calculate it right from the manufacturing floor, the margin of my factory, then I can figure out a net cost. This applies, by the way, to revenue, profit, or any other sort of marginal analysis my business situation might require. There are marginal changes for supply and demand, and their consequential effects on revenue and profits. There are marginal effects to returns on investment. So there are lots of marginal analyses pieces we can do. But they all come back to just doing an integral. Suppose I have a velocity equation. V of t. Velocity of my object at time t, and I'll be nice, we'll put that in seconds. So I'm doing meters per second here. If you don't like thinking in meters, think in feet. It doesn't matter. The units are less relevant. What does the integral of my velocity tell me? A crappy sketch might help. If I think of the area under that curve, what units does that area come up with? Meters. Because each little rectangle is meters per second for a height and seconds for a width. That's going to be meters per second times seconds is meters. Which means this represents what? Distance. Let me do an example. I have a velocity equation. Minus 32t plus 64. I want the distance over the first 4 seconds. Please do the integral. Come on, you can do this one. By the way, this problem originally, I believe, was phrased in feet rather than in meters, but the units are irrelevant. my antiderivative. The antiderivative of t is what? Well,
What if you-
there's more.
That's negative 16.
16t squared, because it's t squared over 2. So the 32 is going to become a 16. And then 64 is going to get, so plus 64t from 0 to 4. When I put in 4, 16 times 16, 256, plus 64 times 4 is also 256, minus, plug in 0, I get 0, plug in 0, I get 0. What? That's right. But here's where I come up with a problem with our answer. It isn't the fact that the answer is 0 that's a problem. It's that the comment up there is distance. This isn't distance. What is this? It's net change. So it's not distance, it's how far I am from my starting. In this case, my object went to the right and then came back to the left and ended exactly where it started. If we graph our velocity equation, we actually see this picture. And now my 0 makes perfect sense because the areas of these two triangles cancel each other out perfectly. Each triangle has a height of 64 and a base of 2. And that means the area is the same in both of them, but one is positive and one is negative, so the total area must be 0. So this really isn't distance. It's, in physics terms, the word is displacement. It's how far I end up from my starting point. Now, I will say, if I think of this in feet rather than meters, then that negative 32 is not a randomly chosen number. That negative 32 is the acceleration due to gravity in feet per second squared. So this is the velocity equation in feet. Instead of going left or right, we were going up and down. And we ended right where we started. What if I really want to know how far did it go? How can I fix this so that it actually gives me the total distance, not just the difference in the distance? I need to count distance up separately from distance down. Now, this particular case is rigged because we went the same distance up as we did down because our total displacement was 0. But let's assume that that might not always be the case. Then I really care not about which direction I'm going, but just that I'm going, right? So I need to treat distance up and distance down as if they were really pointing the same way. If I think of distance up as positive, then distance down is negative. If I want to switch negative numbers to positive numbers, what mathematical thing can I do to do that? Say it again. Absolute values. I can take the integral from 0 to 4 of the absolute value of my velocity. But that means I need to know where it changes from negative to positive or positive to negative. I need to know what these are. So I go back and I look at my v of t, negative 32t plus 64. And if I want to know where that changes from negative to positive, I need to know where it is at 0. Just like our critical numbers and our sign charts and all that fun. Minus 32t plus 64 equals 0. When does that happen? What t value makes that 0? 2. And if I pick a number smaller, if I put in t equals 0, I get positive 64. If I put in t equals 3, I get negative 32. Okay, wait a minute. Between 0 and 2, the positive part, I get the same thing, right? The absolute value of a positive number is the same number. But on the negative part, I want to switch that negative to a positive. I multiply by minus 1. So really, my integral, now I get to use one of that crazy property of integrals that I haven't used yet. I can break up an integral in the middle. Instead of going from 0 to 4, I'm going to go from 0 to 2, and then from 2 to 4. And then I can put the actual formula in there where I see the absolute value v of t and it's positive. I can just replace that by v of t. But here's where I know it's negative. So I'm going to replace that with minus v of t. Now put the equation in. There's the absolute value part being done between 2 and 4. Oh, okay. This is going to give me negative 16t squared plus 64t from 0 to 2. I'm going to take this minus sign and pull it out front. Negative 16t squared plus 64t from 2 to 4. Now let's plug in the numbers. For this one, first I plug in 2. 2 squared is 4. Negative 16 times 4 is negative 64. 64 times 2 is 128. Put in 0. Put in 0, you get 0. Put in 4, and I get negative 16 times 16. That's negative 256. 64 times 4 is positive 256 minus, wait a minute, that's going to be this set of numbers again, isn't it? 64, negative 64 plus 128. Now, why is this better? Well, what happens here? That's 0. That's 0. What's 128 minus 64? So this is 64 minus, that's 64 again, but there's another minus sign in there. Oh, 64 up and 64 down gives me a total of 128 traveled. Instead of canceling out, that extra minus sign is what allowed me to count the two directions as the same. So if I want distance traveled, I need to think of getting rid of the direction part, which in this case means taking an absolute value. Questions? I started here, I ended here. I went 0 feet, meters, kilometers, whatever. But if you hit a baseball and it goes for a home run and you started home plate and ended home plate and you didn't go 360 feet, you don't score a damn thing. I can't just say, I start here, I end here, I don't have to go anywhere. No, you actually have to go all the way around to all the bases to score that run in baseball, even though you're going to start and end. Same. Displacement versus distance traveled. Questions? So that's the why I want to do integrals. They're applicable in so many places where things are changing. But now what this means is I need to look at the rules for taking derivatives. I need to figure out how to do those backwards. So we had trig functions and inverse trig functions and the power rule and adding and subtracting. But multiplying and dividing, product rule and quotient rule, those were ugly. Chain rule. I got to figure out how to do these backwards. And that is actually going to take a little bit of work. And believe it or not, the easiest one to do backwards is the chain rule. So tomorrow, I'm going to talk about doing the chain rule backwards. And we are actually going to do this problem using the chain rule as well. I will see you all tomorrow. Have a wonderful rest of your day.